In this video, I want to go over some of the major aspects of projectile motion using a quadratic to model projectile motion. And we've looked at a couple examples of this already, quite a number actually of examples, and we even started off our quadratics unit with a projectile motion problem. But I want to go over a few of these things with you just to refresh your memory and maybe clarify some things if you had some misunderstandings. So the first thing I want you to write it here is projectile motion, and then put in parentheses, what does that mean? It means tracking the height of an object over time. Tracking the height of an object over time. So of course, we don't have to do just height over time. We have other things we can track, but for this unit, we're just going to be looking at projectile motion this way. And this particular equation is one that you have seen before. The height of an object can be modeled with the quadratic 1/2 of g times t squared plus vt plus h sub 0. This 1/2 of g is maybe something you haven't seen before, but we'll cover that right now. But the first thing I want you to notice, class, is if you look at this part right here, if you look at this piece right here, this 1/2 of g, that's your parameter a. This v in front of our variable t, that's your parameter b. And this h sub 0 is your parameter c. So this is actually a standard form quadratic. One more thing to cover with you is the reason that we put this little small 0 here, that doesn't mean the 0 power. It's not an exponent. It doesn't mean anything except for we see that we're already using the letter h in this equation. So if we use h again and we want to make sure we know we're not talking about the first one, then we put a 0 in the front of it to designate that's a different height. Actually, it's a special height or a certain height, and I want to talk about that in a moment. So what are the parts of this equation? Well, h equals, if I can get this to write actually neatly, hang on while I look for my marker. H is the current, my goodness, I'm having a real hard time writing, apologize for that. It's the current height of the object, whatever it is, football, baseball, soccer ball, anything that we're actually launching into the air. It's the current height of the object. This equation now is going to project what that height is. Alright, let's take a look at 1/2 of g. G is actually gravity. So this actually stands for gravity. The effects of gravity, and the reason it's negative is because the parabola is going to be upside down. Our a value is going to be negative. And something you want to know here about this, usually gravity is going to be measured with 2 units of measure, either in feet, the effects of gravity on the height in feet, or the height in meters. And if the height is in meters, then 1/2 of g is going to be negative 4.9. So that's going to be if we are measuring our height in meters. And we're going to be using negative 16. That is 1/2 of g if we're going to be measuring our height in feet. Okay, next one. Let's pick a different color to make it a little bit easier to read. The next one is going to be this v value. We've gone through this before. V stands for the initial velocity. How fast is that object going when it begins its flight? If a soccer player is kicking a ball and they want to kick it a short distance, the velocity is going to be low. When they want to kick it like a goalie, kick it halfway across the field, then the initial velocity or the initial speed is going to be very fast. That's our velocity. And then the last one is, what is h sub 0? H sub 0, that is our initial height. And we can also use the word, instead of initial, we call it starting height. We could also call that velocity starting velocity, because initial means the beginning or the first. Initial or starting height. So you can see the reason we use h sub 0 is because the starting height is a specific value. The h represents whatever the height, whatever is the height of that object at different values of t or different times. So there is our projectile motion equation broken down. How does it play out as far as a graph? On your graph, go ahead and label the y-axis as height and the x-axis as time. We're not going to write down specifically whether it's feet or meters or whether it's minutes or seconds. Just figure that we're going to do time on the x-axis and we're going to do height of the object on the y-axis. And let's put a few points here now. Let's put a point, I don't know, how about if I can find my pointer, let's put one right here. And then let's go a little ways. I'm just going to make up something. Let's put a point right here. And then 1, 2, 3, 4, 1, 2, 3, 4. That's going to be our axis of symmetry. Okay, so let's put another point about right here. All right. Let's kind of project where this particular object is going to be going. So you can probably do a better job than I can. Let's go ahead and usually I tell you guys how to do this. You use a nice light line to sketch this out. And in fact, you know what? I'm going to try something real quick. I learned something new. Let's see if I'm able to do this. I'm going to pick this. Put a line across here. I'm going to make it a little bit thinner. Alright, actually that worked out pretty good. So you go ahead and sketch something just like I did. I learned a new trick. So there's a model of the height of our object over time, and I want to mark a couple things on this graph to show you. Hopefully I can write on the graph to where you can tell what it says. I'll try to pick a dark color. Okay, this point right here, that's our y-intercept. I'm just going to put y-I-N-T. So our y-intercept, that's our starting height. Starting height. You take a look at this. Since time is at 0, that's where the object is before it actually gets launched in the air. And that's actually h sub 0. h sub 0 is our initial height. That, if you look at our quadratic, is the c value of our standard form. And there's our initial height of whatever our object is. Now, here's something really important. Let's label the vertex. And I'm going to put an arrow up here like this because I want to show you a couple things about the vertex. Okay, so let's pick a different color so we don't get it mixed up with the definitions here. So this is the vertex. And here's two things you want to recognize about the vertex. The x value equals time, the time it takes to reach maximum height. I'll just put max for maximum height. So if you look at this, the x value of the vertex is right here on our graph. That's how long it takes for our object to get to the very highest point. And the y value of the vertex is equal to the maximum height reached. Maximum height reached. And I wish I had put this back a little bit. Let me just kind of move this over. The maximum height reached. So take a look at this at our vertex. Right here is the y value of our vertex. That's how high the object gets before it starts coming back down again, the maximum height. So take a look, class, the vertex. You need to understand the vertex is telling you The x value tells you how long it takes for the object to reach maximum height, and the y value tells you what that actual maximum height is. Then there's one more point on the parabola we want to recognize, and that is this one right over here, and that is the x-intercept. And the x-intercept, this tells you the time it takes to hit the ground. Now, not all of our projectile motion problems will actually have our object hitting the ground. Sometimes it has to actually reach something, or maybe it's going to go below ground because it's going into a hole. But in general, the x-axis is the ground, and when the object hits the x-axis, or the parabola hits the x-axis, that's telling us how long it took for the object to actually land back at height equals 0, which normally is the ground. Okay, so there's some basic things about the parabola. Now let's apply this knowledge to a problem. So now we're going to see our word problem. Fred throws a football, and the height of the ball in feet can be modeled with the equation f of t equals negative 16t squared plus 28t plus 4, where t is the time in seconds since releasing the ball. So a couple things we see here in number 1, we're measuring height in feet, and we're measuring time in seconds. And you can see, class, that this equation matches up with the one over here. F of t actually represents the height of the object. Negative 16 is our gravity. 28 is our initial vertical velocity. And our number 4 is our initial height. And the one thing I didn't say is over here in blue, when it says initial velocity, we should put on here vertical. So let's add something here. You might want to erase this. Instead of just initial velocity, it should actually say initial vertical velocity. Because the only velocity we're caring about at this point is the velocity up and down, not side to side, or not horizontal velocity. All right, so our first question, what was the initial vertical velocity? Well, how easy is that? Initial vertical velocity of the ball. We know the initial vertical velocity is 28 because that is the v in our equation, which happens to be our b parameter. So we're going to say here, put a little note here, this is the b parameter. That's the b parameter. So our answer is going to be the initial velocity was 28. There's our b value. In this case, it's going to be feet per second, because feet is how we're measuring height, and seconds is how we are measuring time. Maybe you want to just go ahead and write out the word feet. I have space for that, so I might as well do that. So 28 feet per second. All right, first question, easy. Second question, what was the initial height of the ball? Well, initial height is our starting height. That's h sub 0. That is the number 4. So this is going to be the c parameter. The c parameter, which in this case is 4. So our answer to this one is the initial height was 4 feet. And remember, we're measuring our height in feet, so 4 feet was our starting height. And that makes sense. Person's throwing a football. They're not throwing it from ground level. They're throwing it from wherever their arm is, and this person, whatever their height is, they're throwing at a starting height of 4 feet. All right, next question. And let's underline this. How long did it take for the ball to reach maximum height? When you see the word maximum, class, you know in a projectile motion, that's the vertex. And how long, that's a measure of time. Time is the x value of the vertex. So we're going to put on here, what's our help here? This is the x value of the vertex. The x value of the vertex is going to tell us how long it takes for the object to reach maximum height. This is a standard form quadratic, and we know that the x value of the vertex is found with negative b over 2a. Let's take a look at our b value. Our b value, let me scroll back, our b value is 28. So that means our negative b is going to be negative 28 because b was positive. And then we've got 2 times a. A in this case is negative 16. There's going to be our x value of our vertex. Remember, I've taught you that you always, if you've got multiplication in the denominator or the numerator, just do that first. Let's go ahead and do 2 times negative 16. So 2 times negative 16, and that's negative 32. So I've got negative 28 over negative 32, and let's multiply that out. Negative 28 divided by negative 32. Negative times divided by a negative is a positive 0.875. So I'm going to put 0.875. Now think about it. How long? Our unit of measure here is seconds, because how long is a measure of time, and we're doing time in seconds. So our answer here is, it took, you can write this sentence any way you want. I just follow the question. It took 0.875 seconds to reach maximum height. I'll just put maximum height. So pretty simple, just the x value of the vertex. And then last question they have on this page is, what was the maximum height? Now notice there's nothing about time anymore. Now we're talking about maximum height reached. Well, take a look at our example. The maximum height reached is the y value of our vertex. So to find the y value, we have to plug in the x value, and then we'll be able to get the y value. So let's plug in our x value. We're going to write our function. This is f of x, and our x value is going to be 0.875 because we want to know how high the object is at exactly 0.875 seconds. And let's plug this in. We got negative 16 times 0.875 squared plus 28 times 0.875, and then we've got on the end plus 4. So take a look. I just took our equation and I plugged in t, which was 0.875. Now put that in your calculator. Let's go ahead and do that together. So I've got negative 16, and then in parentheses 0.875. Oops, it's backspace. Close our parentheses. Let's square that. Then we've got plus 28, parentheses, 0.875, close parentheses. And now we've got plus 4 and press equal. We've got 16.25. 16.25. Now think about it. This is the maximum height. Our height is being measured in feet. So the maximum height of this particular ball is going to be 16.25 feet, and I'm going to write that as a sentence. The maximum height, and I'll just put max for maximum. The maximum height reached was 16.25. Make sure you get your unit of measure, feet. So now you see from this example that we can use a bunch of things from the equation. We've got initial vertical velocity, the initial height. We can use the vertex to find how long it takes to reach maximum height on our graph. and we can use the y value of the vertex to find what was the maximum height reached. There's one more thing we haven't covered in this video, and that is, can we estimate how long it took for this particular ball to reach the ground? And if we had a scale on our axes, if we actually graph this, we could just extend the parabola down, figure out about where it crosses the x-axis, and use that as our estimated time it takes for the ball to reach the ground. So hopefully this helps you as we kind of go through some of the basic parts of a projectile motion question.